So here we can test it. So we can set some values here and print the weights. So we have weights here as contains, it's just a vector. It contains weight 1 from here and weight 2 from here. So those will be our initial weights, and then we're going to run update weights. And remember that we said that what's returned here is a list, and basically the list has the new values, and it also, we give them names, W1 and W2 as the list element names. So anyway, we can run that here, and we can use these weights from this vector. We can access them with this, the first element and the second element, and put them into this update weights function. And then remember that it returns a list, so we'll call that list weights list. That's what gets returned by this function. And now we can access the elements from this list by doing this. Remember, the double brackets gives us just the values. So we're accessing just the values of these double brackets give just the values. And so we're accessing just the values of this weights list, not the names. And so we'll print weights updated, and then weights, and we'll see what we have in there. And this is what we have. So have the weights changed? Yeah, by a little bit. This one increased a little bit, and this one also increased a little bit. So in our search for the lower value of the cost, we have tried to move down the cost curve, and in this case, the W1 weight was increased somehow, and the W2 weight was also increased. Okay, now let's go into the details of this this update weights function that we're writing. So for better or for worse, we're relying on a weights vector being already created outside of the definition of this function. So that's just the way this function was written. So we need to have this defined outside. But let's continue. And this says we're going, it could be created with something like this. So I don't think we've mentioned this function, but maybe you've seen it elsewhere. This is just a random number generator, and it's generating it from what we call a uniform distribution. You could be generating it from like a normal curve, but anyway, it's generating it from a uniform, and that's what this UNIF means. So that's the name of this function. It's basically a random number generator, and we're going to generate two elements, and both of them are going to be between -1 and 1. And so that will return a vector, and we'll assign it to this, and then we have created a vector with two random weights in it to start with. Then we also have a comment here that says, after running this, its output is assigned to a list named weights list. So that's what we saw here. After we create the function, we run it, and we assign its output to weights list. Of course, you could call that anything. You don't have to call it weights list, but it's going to be a list with the weights in it. And then, as we said, we can update our weights, and we're going to create a weights function outside, weights vector outside of this function. And now we can update the weights with what's in weights list. So this is just kind of giving us instructions on how to use this function after we create it. So now here's the code, and remember that this calls for several values, this, and this several arguments, and this one also. So there's going to be an x value, a weight 1 value, a weight 2 value. So we're going to take the X value and the weight 1 value, and we're going to multiply those together. This is occurring within the definition of our function, update weights. And then we're going to do all the things that we normally do. We're going to take sigma of that, assign it to here, multiply that by the second weight, get Z3, put that into sigma, get Y hat. We're also going to calculate the deltas here, the delta 3 here, and then we can just multiply delta 3 times A2. We saw that's the formula for the JdW2, the derivative of J with respect to W2. And then we're also going to create our delta 2 function, which actually we use delta 2 constant. And actually we use delta 3 as part of that definition. And then we also do this, and you can go back and make sure this is correct. And so we do this, and then our derivative of J with respect to W1, we recall was delta 2 times the X value. And then we have we've now calculated, defined this, and defined this, and then we can use that and that to update. We'll take the old values and create the new values for W1 and W2. And then we can take W1 and W2 and wrap it in a list, or make it into a list, and call that the returned list. And we can give it names here. We'll call it W1 and W2, and then those are the names of the elements of the list. And then we're returning the list. That means the output of this function is, as we said, a list. So that means we can assign the output of this function to something, and that something will be a list. And that's what we do. We assign the output of the function to here, and this something will be a list. And we can access the elements of the list, the first element and the second element, and then we've now updated our weights vector, and now we can print out our new weights. Okay, the next thing we're going to do is we want to read in the entire data set, or an entire data set. So we don't want to do this just for one element or one example in our data set. We want to read in the whole data set. Each time we're going to update the weights, and so hopefully by using many examples, we're going to train our network to make decent predictions. Now, it's not really going to work that well because this is such a basic neural network, right? We're just a 1-1-1. That really is not much of a neural network, so it's probably not going to give us great results, but that's the idea. So the entire data set, we're going to use this data set here, and this is a data set about wine prices and the wine ratings. And the original data set is available from here. There's a couple different versions there. We're going to use the one that's described here. I saved it as a CSV file, or maybe it was already a CSV file. And we're going to filter out so there's many different types of wines in this data set, and we're going to filter out just the Chardonnays. So we only want those. So we're just trying to, I don't want to use the whole data set here. Just want to use maybe 1,000 elements. I don't know how many were in the original data set, but if we just use the Chardonnay type wine or variety, then that's going to be far less than the whole data set. And further, we're going to filter it only wines that come from Australia or New Zealand. Here's the OR operator, and you can read this and you can see that we're filtering out, we're only taking wines from Australia and, or New Zealand. So we now have the reduced data set, which we have in this wine variable. And you can see here that I think this was the original data set. No, sorry, this is our data set. These are the column names. So there's something called X1, there's a country, there's a description, designation, points, which is a measure of how good it is, how the rating, the price, the province, region 1, and so on. So we are only going to choose the columns points and price. So we're only going to have two variables, that is only one input variable here. So this is a very simple task of, I think it is predicting the price. I think that's the output variable from the points. We'll see if that's true or not in it as we scroll down here. But I think that's the task, is to try and predict the price from the points. Now that's very unlikely that we could do a very good job with that. But anyway, that's just our practice task here. So after all the filtering that we did, we can check to see how many rows we're left with. We're left with this many rows. That's how many rows we have in our data set. And then we want to make sure that we have complete cases. So we're just going to drop anything that has an NA in it. And we've used this method before, the complete cases function. I think it's from the mice package. And so now after we do that, then wine has only this many. So we filtered out some of the rows. Okay, now we have we want to split the data into a training set and a test set. And one thing we're going to use is a function called floor, and that rounds a number down. So if you take a number like 2.8 and you put it in floor, it'll give you 2. So it cuts off the decimal part of a number. So again, if you have 2.8 and you put it in here, it'll become 2. It'll return a 2. So it just deletes the decimal part. It doesn't round it up or round it down. It just cuts it off, cuts out the decimal part. So anyway, we're going to take from the number of rows, which we said was here, we're going to take 75% of them, and then we're going to take floor, so we just get an integer out of this, and that's going to be our sample size. And then this, we set the seed at anything, but this just allows us to get reproducible results. And so hopefully if you run the same code and you use this set seed with this in there, you'll get the same results that I get, that I get in the text. So anyway, so now we take, so we defined sample size, and now we're going to use the sample function, and I guess that takes one of the arguments, or one of the parameters is the sample size, the size of the sample. So we're only going to take 75% of the elements, and we're going to sample, I believe what this does, well, you can check what this does, but basically we're going to get a train index. So let's see that. Let's see what happens next. Creating a training set and a testing set. Although we split the data into training and testing sets, we do this just as an example. In this example that we're doing, we're not actually going to use the test set. But this method we're going to use many times, or this set of steps we're going to use many times. We're going to just start using it here. So we take the train indices, so that's part of the data, and we're just going to filter out those rows from our wine data frame. And then this gives us the other ones, because this is minus the indices, and so that will be our test set. So this is going to give us our training set. This is what we're going to use to train our neural network. Then we could test it with the remaining data to see how well it did. But this is such a primitive neural network, it's not going to be too impressive. But you could test it. You could use the test data set to see how well it performs. So in this modeling task, we will predict the price from the points. So we're going to create, for the score, we're going to take the score column, we're going to make a vector out of it, and the price column, we're going to make a vector out of that, and we're going to normalize both of them. Now there are plenty of functions in R that will normalize your data for you, but we're just going to write our own right here, because most of them use something like this. Maybe not exactly. There are several different ways to do this, but one of them is this procedure that we're going to use. So we have a fraction here. You can see there's a division sign here. And the denominator of this is going to have this. So it's going to have the maximum value for the variable minus the minimum value. So that's going to give you the distance, the maximum spread within that variable. So, and then here you're going to take the value that you're trying to normalize and subtract the minimum value from it, and then divide by this. And then we are going to take that whole thing and subtract 0.5 from it. And so what we're going to get is all of the entire set of values of our variable are going to be mapped to this interval between minus 0.5 and 0.5. So go through this and make sure that you understand how this works. But basically it takes a variable which could go from let's say 0 to 1,000,000, and then it's going to map all of those values to something between negative 0.5 to 0.5. That's called normalizing the variable. So we call this function normal 0.5, and we're going to use it. So we're going to take the training data and just focus on the points variable and call it points, and then we're going to normalize this points vector and reassign it to points. And we're going to do the same thing for the price variable. The price column is going to be set to the variable price, and then we're going to normalize it and reset it to price. Okay, so we said we want to train the neural network on the entire data set. So, so far our update weights function was only used once, but we're going to use it once for each element in the data set, or for each example. And then we're going to do something a little bit artificial. We're just going to use this newly created neural network to make a prediction on just a single value. So it's not really very interesting, but that's all we're going to do. So the x value is the parameter name for the single variable, and we will make a prediction. And anyway, but the default value for this x value is 0.9. Now here we're using this x value. I think we had in the update weights function, did we have something called x value also? Yes, unfortunately that's a poor choice of variables, because this x value, well, maybe it is the same value. Anyway, let's continue. Anyway, this x value is just, at the end, we're going to make a prediction. I mean, we're just going to assume that the x value is 0.9, or we can put whatever we want in here, but the default value is 0.9. Now, remember that we are predicting the price from the points. So we're saying, suppose that the points were normalized. Suppose that the points were 0.9, then what would we predict the price to be? So this is a little bit artificial, but let's just continue. So we're going to write now a new function called predict neural network for a single value. So it's just for one single value. See, this function is a little bit clumsy. You have to put in a single value, and then it will predict, oh, well, if the single value is 0.9, or whatever, you can fill this in with anything you want, then we will predict that the price is something. That's the way this function is designed. Now we're going to have to go through the entire data set. Even though we're at the end, we're only predicting a single value. We're training the network on the entire data set. So we're going to have to go through a loop. So we're going to have a looping variable. We're going to set it initially at 0. And the initial values for W1 and W2 need to be set prior to running this. So we have to set up W1 and W2 before running it. That's the way this function will be written. Note that this function updates the weights each time it reads in a new example from the training data. In a future version of our algorithm, so I think in the next chapter, I think, we will create what's called a batch function, which waits to do the updating until reading in the entire data set. So in this current function, each time we read in a new example, we're going to update the weights. But there's another way to do this. It's called using a batch function. And basically, it reads in the entire data set and then updates just once based on the entire data set. So that sounds a little hard to imagine, and it's a little bit complicated to explain, but we are going to go through it in full detail. But for now, we're just going to update after each data set after each example is read in. And furthermore, note that input x, so here, input x is the parameter used for the training set data. So it's the input data, which we said was the points, whereas the x value is the parameter to hold a new single test value for which the network will make a prediction. So maybe we should check how this works. So here's the results. Once we write the code for this, here's how it works. So pred single value. So our input data is the points, and the output data is the price. And the x value, we're going to set it to 0.2, and the learning rate is going to be set to 1. So what's this going to output? It's going to output some text here. It's going to tell you the number of rows in the data set. Then it says, given the input of 0.2, so given that we have this input with a learning rate of 1, the predicted output would be this. So this says that if the x value, that is, if the points were set to 0.2, then the predicted price would be this. Now we have to interpret what this really means, because this was all done, was all normalized. So we're getting the normalized predicted output. Because what does this mean? Does this mean only 18 cents for a bottle of wine? Probably it doesn't mean that. And does this mean that the points were only 0.2? Probably that's not what this means. Anyway, so this is the output, and these are the kinds of things you have to feed into the function to run it. So now let's see how the function is called. Okay, so let's take a look at the structure of the program, or of the function. So this is what we call the function signature here. Here's the simple sample call. And here we start with, we're going to run this through a loop. So we have a loop variable, and we're initializing it at 0. And here is where we internally set the weights to random weights. Now we say for input in input x. So input x is here. So this is the entire set of examples and just the points for the examples. So this is an entire vector of the points for all the examples. We can see that points here is the entire points column. So we're saying for input in there, so this is going to take the first points example, and then the next one, and the next one. Here we increment the counts, and we get the current price. We take the count from, and we take the output vector, which is here. So it's the price vector here. Price is here or here. So we're going to get the price, and then we're going to run the update weights that we've already written here. And we have to make sure that we have the right inputs into update weights. So we should go back and check the update weights function signature. So here I have the split screen here. This is the original update weights. Here's an example of the call. So what goes in first is the input value, and then the first weight, then the second weight, then the associated Y value here, and then the learning rate. So we need to fill in all of those here, but we're running this within this loop, and so that there are certain values or variables floating around already created, and we need to fit those into the call inside this loop. So here we have, so input comes from where? You can see input comes from here, so it's the point, it's the, input is within the loop, so it's the current input. Where's that loop? Here. For input in input X. So input is the current value of the input, or the current value of the points. So that goes in here, which is correct because we need the X value there. And then weights comes next, and that's from, we have this weights vector here. I'm sorry, yeah, vector here. And this is the first element, so that's the first weight. And this is the second element, and that's the second weight. So that's correct because we're supposed to have the first and the second weight. And then the current price, so that's the Y value. And that comes from here. And then we have the learning rate, which we've defined somewhere. And then when we run all of that, we can update our weights list. And now we can use our weights list to update our weights. Now, then we go back and we run through the loop again. Now, fortunately, we never engage this statement again. So we're not resetting the weights randomly ever. That happens only at the beginning. But then the loop keeps updating the weights for each example in the data set. And we go through the entire data set that way and updating the weights each time. Now, finally, at the end, we have our final set of weights, and we run through this to generate the Y hat prediction, and that's based on the X value. So where was the X value? Here. So this is that arbitrary X value that we're going to enter, and then we just want to see what the prediction would be for that. So we get a Y hat as the prediction, and we print it out. We return Y hat. So we print this, we print this, we print this, and we return Y hat. So to get this value of Y hat and print it onto the screen, we have to set this equal to something. So let's see how we do that. No, I apologize. That's not right. I think it will just print out this when we return it. So when we run this here, it's going to print out all of this stuff first and then return y hat. So y hat will actually be printed out here. So here we do it with a x value of 0.2, and we get a predicted here. And here we do it with an x value of 0.9, and we get a predicted value of this. So as the points go from 0.2 to 0.9, the price goes from here to here. So at least the price is increasing. Now, how can you figure out how to interpret the price here? So what does this mean in terms of the price? This is our price variable, and also you could say the same. Similarly, what does this mean? So this is the points, but there are no. If you look at the data set, there are no points of 0.2. The points are much higher than that. Remember, this value has been normalized, and this value has been normalized. So even though the price variable might go, let's say, from $10 to $100, this normalized value, we said, only goes from 0.5, from negative 0.5 to positive 0.5. So this is more than halfway through that interval, because 0 is right in the middle of the interval. This is more than halfway. So this represents a price that is more than halfway through the entire range of prices, and this also represents a so one question you should be able to answer is, how can you take this normalized value and interpret it as an actual price, a dollar price? So you should be able to figure that out by sort of unraveling the way we normalized the values. So basically just go backwards. Now here we experimented with a very different learning rate of 25. Now typically that would be much too big, but we just experiment with it. And now things don't really work that well, because with this 0.2, well, I can't say that it doesn't work that well, but anyway, with 0.2, we now get a predicted price considerably lower than what we got before. Anyway, a learning rate of 25 is probably very unreasonably high. Okay, the next topic is epochs. So although it may seem odd at first, we can actually train the weights again with the same set of training data. So we just feed that training data into the neural network again. Each repetition of the training with the entire data set is called an epoch. And typically there is another parameter in the function signature, which we can call epoch, and which may be set to a number like 500. So we may want to train through 500 repetitions of the data set. So meaning we would run the same training set through the network 500 or more times. This will generally improve the performance on the test data set, but you can't necessarily guarantee that it's going to improve the performance on this will generally improve the performance on the training data set, and hopefully will improve the performance on the test data set. However, our network is very primitive. At this point, it's only a 1-1-1 network, and we need to develop further. Most neural networks have more nodes in the hidden layer, and we'll build our next network with a 2-3-1 architecture. So the next network we want to code, or we want to understand and then to code. But first we have to do the mathematics, look at the matrices, and then we want to code it.